All right, so this is a death packet review. This is going to be the video for questions 1 through 10. So this will be videos for questions 1 through 10. And we're not going to work all of them, but we'll work the ones that were requested or try to get through as many as possible. So question number 1. Suppose the manufacturer knows that 20% of the circuit boards coming off the assembly line have a minor defect. If an inspector keeps inspecting boards until he comes upon one with the defect, what's the probability he'll have to inspect at most 3 boards? So basically, we're going to continue until we find one. So since it's a continue until he comes upon one, this lets me know that we're looking for the first. So this tells me we're looking at a geometric. We have a geometric distribution. We know that our probability is 0.20 and at most 3, which means it could have been, so the probability that x is less than or equal to 3. So in other words, if we made a number line, it could be number 1, 2, or 3. And since we have multiple values, this makes it a geometric CDF. So the way I would show this is for my work is I need to show the first one, and I need to show the last one. Well, the probability of success on the first one is just 0.20. The probability on the last one means I've needed to have a fail and the success. Well, my success is 0.2, and I need to have had 2 failures. All right, so this will be work shown. What I'm going to plug into the calculator is this, Geo CDF 0.2 and 3, where this is my probability, this is my x. This is not acceptable work. This is just what we're plugging into the calculator, all right? So plugging that into the calculator, second vars, geometric CDF, probability is 0.2, x is 3, and I end up getting 0.488. All right, so I end up getting 0.488, which happens to be letter C. All right, I'm going to pause my recording for just a second. So the question was, how did I determine whether or not this was a geometric CDF or a geometric PDF? Well, it said it could be at most 3 boards, which means it could have been 1 board, 2 boards, or 3 boards. So because it could have been multiple boards, any one of those, it's a CDF. If it was specifically occurring on the 3rd board, and I only circled the number 3, that would make it a PDF. So when it's a singular value, it's a PDF, but when it's a multiple value, it's going to be a CDF. 4. All right, so this is question number 4. A plumbing contractor obtains 60% of her boiler circulators from a company whose defect rate is 0.005, and the rest from a company whose defect rate is 0.010. If a circulator is defective, what's the probability that it came from the first company? All right, while this is not specifically a distribution problem, this is something that we've done before. So looking at this, we end up with 2 companies, and we have 2 things we're talking about. We have a defect rate and a non-defect rate. So we have company 1, company 2. The probability that it came from company 1 is 0.60. The probability it comes from company 2 is 0.2. Doesn't matter which one you have. And then we have defect and non-defect. So this defect is 0.005, and the rest come from 0.001. So 0.60, 0.005. That's going to make that 0.995, because all I did was bring those numbers straight up. I'm going to bring these numbers straight up. And the defect rate for company number 2 is 0.01, which makes this 0.99 because it's 1 minus that. So when I mess with the defectives, 0.6 times 0.005. So this gives me the probability that it came from them and was defective. And 0.4 times 0.01 gives me the probability that it came from this company and was defective. So we end up having 0.007 probability of defects, what they asked for. If it's defective, so given that it's defective, what's the probability that it came from the first company? All right. So given that it's defective, given we always are going to have an intersection, probability of defect is 0.007. The probability it came from company 1 and was defective, or the intersection is that. So 0.003 divided by 0.007. So 0.0429 approximately, or 0.429, excuse me. All right, I'm going to pause that one. All right, this is death packet question number 5. A company bids on 3 contracts with probabilities of winning the contract of 0.1, 0.25, and 0.3. What's the probability of winning at least one? Okay, first off, this is in here to be a little bit tricky. To be a geometric or a binomial, it must be a Bernoulli, which means the probabilities have to be the same. Well, the probabilities here are not the same, so it's not that. But we can do this because we have each individual probability. And it says, what's the probability of winning at least one? All right. So at least is always going to be 1 minus the complement situation. All right. So basically, we're going to find we could either win 0 contracts, 1 contract, 2 contracts, or 3 contracts. So we want to win at least 1. So either 1, 2, or 3 is adequate. The easiest way is do 1 minus the probability of winning none of the contracts. Well, what's the probability I don't win the first one? 0.1. The probability of not winning the second one is 0.25. Oh, these are probability of winnings. These are probability of winnings. So I need to turn those into probability of not winning. So not winning is going to be 0.9, 0.75, and this one is going to be 0.7. So the probability I win 0 of them is going to be 0.9 times 0.75 times 0.7. That's the probability of winning 0 of them. So then I do the at least part. So that should give me my answer. So in this case, 1 minus 0.9 times 0.75 times 0.7. So we end up getting 0.5275. Okay, this is question number 6 on the death packet. Suppose 2 events E and F have non-zero probabilities and they're P and Q. Which of the following is impossible? All right. Which of the following is impossible? So when we look at this, we have P plus Q is greater than 1. If P plus Q it's possible the probability of one is 0.5 and the probability of another is 0.7, so that's possible. It could be 0.5 and 0.7, in which case we end up with negative. It could be that P was 0.7 and Q is 0.5, so the ratio is greater than 1. But remember, events cannot be mutually exclusive and independent. this is impossible. This is impossible unless, this is impossible unless one of them is 0. And since one of them are 0, since none of them are 0, this is not possible. This only can occur if one or both of the events' probability is 0. So independent and mutually exclusive in general is impossible. Okay. Suppose 80% of jurors come to a just decision. In a jury of 6 people, what's the probability that more than half come to a just decision? So real quickly, 1, 2, 3, 4, 5, 6. More than half would mean that I need 4 or more. So we would need 4 or more to come to a just decision. So basically, I have a PDF of 4 plus a PDF of 5 plus a PDF of 6, or I can do an at least math. So let's determine what type of distribution we have. Well, we have a fixed probability and we have a fixed number of trials. Because we have a fixed number of trials and a fixed probability, we're working with a binomial. And if I'm showing my work for the test, I'm going 6, choose 4, 0.8 to the 4th, 0.2, which is 1 minus that, to the 2nd, because 6 minus 4 is 2. That's that's the probability of a 4. Plus, dot, 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 plus, 6, choose 6, 0.8 to the 6, 0.2 to the 0, 6 minus 6 is 0. So that would be work shown, and that would get me full credit as far as work shown. But what I'm going to plug into the calculator is 1 minus the binomial CDF of trials of 6, probabilities 0.8, with an X value of 3. So here we go. 1 minus second vars, binomial CDF, trials is 8, trials is 6, probability is 0.8, X value is 3. Now, a couple things. I knew it was a CDF because I circled more than one value. If it had been one value, I circle a PDF. And I always subtract out the highest number I don't want. I want 4, so don't take 4 away. The highest number that I'll let you take is the one that I don't want, which is 3. So I end up getting 0.90112. Moving on. Oh, let me pause that for a second. Okay, moving on to problem 8. An inspection procedure at a manufacturing plant involves picking 3 items at random and then accepting the whole lot if at least 2 of the 3 items are in perfect condition. In reality, 84% of the whole lot are perfect. What is the probability that the lot will be accepted? Well, first off, we have a specific number of trials and we have a specific probability and we have a fixed probability. So this makes this a binomial. And we're only selecting 3 items. 2 of the 3 are good, we accept it. All right, so I have multiple values circled, so this is going to make it a binomial CDF. For work shown, 2 and 3 satisfy. So basically, 3 choose 2, 0.84, the 84% that are actually good, to the 2nd, and then 0.16, 3 minus 2 is 1, plus dot, 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 plus 3 choose 3, 0.84 cubed, 0.16 to the 0. That's supposed to be an 8.4. All right, on the calculator, because we have gaps at the bottom, we're going to go 1 minus, and we're going to subtract out what we don't want. So 1 minus the binom CDF. Trials is 3, probability is 0.84. X value is, X value should be a 1, because that's the highest value that we don't want. Please remember, calculator commands is not adequate work shown. You must write the, you must plug into the equation in order to receive credit. So 1 minus second vars, binomial CDF, trials is 3, probability is 0.2, X value is 2. And we end up getting a probability of 0.512. So obviously I have an error. What did I do wrong? Oh, second vars, normal, second vars, binomial CDF, 0.84. Well, that's disappointing. Pause this for just a second. Well, I goofed up, guys. I input the data wrong. So second vars, so first off, 1 minus second vars, binomial CDF, trials is 3, probability is 0.84, and our X value is 1, which is not what I plugged in. That should have been a 1. When we do that, we end up getting a 0.931. All right, we ended up getting 0.931. I apologize for that error. I should actually say this. This is problem number 10. This is not something we actually talked about in class, or we didn't talk about much, if at all, and will not show up on this particular test. We will need to know it later in the year, but we shifted it off just because we didn't want to overload with the amount of time that we had. So basically, a binomial distribution, if it has a probability of 0.5, is going to be pretty symmetric in mound shape if you have a if it's a 0.5. On the other hand, if it's less than 0.5, if it's less than 0.5, if it's less than 0.5, this probability right here is going to be skewed right. If it's greater than 0.5, it's going to be skewed left, okay? So which of the following is incorrect? The histogram of a binomial distribution is 0.9 is skewed to the right. It's not skewed to the right. Most of my probabilities are going to be up here, so this one should have been skewed to the left. So this answer is C. And anyway, that's the answer. The reason A is wrong, even though it is going to take on a symmetric, that happens as the number of trials increase. And so even though it's centered at 0.5, you may get a very ugly looking distribution. So the best answer on this one is C. Don't worry about it. It's not going to be on the test.